So in this situation, we have a sphere that is being heated, right? And when, if you've taken a physics class, maybe chemistry class, when metals are heated, they expand, right? So I have this sphere here, and as it's being heated, I know how fast its radius is increasing, right? dr dt is 0.03 centimeters per second. What I want to know is at what rate is the sphere's volume increasing when the radius is 10 centimeters. Okay, so let's see. I'm going to start with a formula, right? I know I'm given information about the radius, and I want to talk about the volume. So I need a formula that relates those two variables. And the volume of a sphere is 4/3 pi r cubed. Now remember, right? Remember these v and r, these are both functions of time, right? The radius after a certain amount of time, the volume after a certain amount of time. So when I differentiate this, I'm going to do this with respect to time. Right? So dv dt is equal to, or this 4/3 pi, that's just a constant. So 4/3 pi d dt of r cubed. Now that's because remember that it's r of t, right? You're thinking in the back of your head. So this is a chain rule situation. This is going to be 4/3 pi times 3r squared times dr dt. Whoops, this didn't reduce my exponent. 3r squared. I said it, but I wrote it wrong. So let's see. Let's simplify, right? Cancel some stuff here. 4 pi r squared times dr dt, and this is my dv dt. Right, so now I can answer the question, right? I know how fast the radius is increasing. That's something we can observe, right? Radius, that's something we can sit here and watch and see how fast it's increasing in one dimension. So I'm going to put these numbers in. 4 pi times my radius, which is 10 centimeters squared, times 0.03. So let's see. 100, 10 squared is 100. 100 times 0.03 is 3. 3 times 4 is 12. So this is 12 pi. Now, if this were a math class, right, which yeah, it is. If this was a math class, I would stop at 12 pi, and I would give some units here, right? This is the volume. So the volume is going to be measured in cubic centimeters. So 12 pi cubic centimeters per second. Now the physics guys, right, the engineering guys, they're not going to be happy with having pi in the answer. So pi is 3.1415. If you put that in there, this is approximately 37.692 cubic centimeters per second. Quite a bit faster. Which hopefully kind of makes sense to you. Remember, if you double the radius of a sphere, the volume increases by a factor of 8. So yeah, we do expect a given change in the radius to have a greater change, a greater impact on the change in the volume. So take a look at this one. We've got a falling ladder, right? A ladder that's kind of sliding down the edge of a building. And yeah, you can take a look at this one, right? See if you can work out what the relationship is going to be. Then start this up again and we'll work through it together. Right, so here's what I have. I have the ground. I have the wall of this building. And I have this ladder. The ladder is here. Okay, and what do I know? I know that this ladder is 30 feet long, right? And I know that it is moving away from the wall, right? So that's this rate of change. This rate of change is 2 feet per second. And I want to know how fast is the top of the ladder moving when the ladder is 10 feet from the wall, when the base of the ladder, right? When this part is 10 feet from the wall. So when this distance is 10. Okay, well, let's get some variables in here. Let's call this distance x. So this 2 feet is dx dt. And let's call this distance y. So its rate of change is dy dt. So what I need is a formula that gives me the relationship between x and y. Well, you can see, I mean, the building, you're assuming it's a standard building, and the wall hits the ground at a right angle. So this is a right triangle, which means that x squared plus y squared equals 30 squared. Oh, excellent. Now I can differentiate. And remember, we're talking about dx dt, dy dt. We're doing this with respect to time. All right, so the first part, 2x times dx dt plus 2y times dy dt equals 0. And it's dy dt that I want to talk about. So let's solve this, right, for dy dt. 2y dy dt equals negative 2x times dx dt, which means dy dt equals negative x dx dt divided by, not dy dt, divided by y. All right, now I can put some numbers in here, right? Because I was asked for a specific, how fast is the top of the ladder moving? That's this rate of change, which is dy dt, which is why I solved for it. So let's put numbers in here, right? I know that x is 10, so this is negative 10 times dx dt, which is 2, divided by, and what is y? Well, again, I'm going to go to the Pythagorean theorem, right? 10 squared plus y squared equals 30 squared. 30 squared is 900. 10 squared is 100. So this is y squared equals 800, which means y is square root of that, 20 times square root of 2. That's the square root of 800 simplified. So I'm going to put 20 square root of 2 down here. And let's see what happens. This is actually coming up pretty nice. 10 times 2 is 20. Right? So these and the 20 cancel. This is negative 1 divided by the square root of 2, which my calculator says, working it out here real quick, this is negative 0.707. What are our units? We're measuring in feet per second, and it's negative. Are we okay with it being negative? Well, yeah, it's going down, right? This top of the ladder over here is going down. So yeah, I'm fine with its velocity, which is really what we found here, right? Its downward velocity being negative. Okay. So I want to think about this for a minute. I want to think about this, and let's go back just to this part, right? Just my formula, right? Eventually, y is going to be 0. Or the ladder is going to make it all the way to the ground, and then y is going to be 0. It's going to hit the ground. It's going to stop. What is dy dt? How fast is that top end of the ladder going when it hits the ground? When y equals 0? I mean, we should be able to calculate this, right? That would be negative 10 times, well, it's not going to be 10. It's not going to be 10 anymore. Let's just leave it at x. Negative x times dx dt, which is 2 over 0. Okay. What's this telling me, right? This is undefined, and this is one case. I'm going to very briefly break one of my own rules and say it's infinity. Okay. What's happening here is what this is telling us is that the rate of change, the downward velocity of the top of the ladder, is unbounded, right? If it's super close, if you put 0.01 in there, right, you would get negative 200x. X is going to be really close to the whole 30 foot of the ladder at that point. That's negative 600. Negative 600 feet per second that thing is falling. I don't think so. I don't think so. It is not going to hit at a faster than the speed of light, crash to the ground. No, it's not going to happen. So what's the problem here? Right? Why is our method not giving us a valid answer? Well, this is something that, and I'm really kind of saying this to the engineers and the physicists and the science people in the room. You always have to be careful with models like this, right? Does the model, because this is an idealized mathematical model, how well does this model match the actual reality? And here's what's happening. I want you to focus on this part here. This ladder has velocity in the horizontal direction. It is, more specifically, it is accelerating. It's speeding up in that direction. Remember from your physics classes, if you've taken a physics class, acceleration implies a force. There is a horizontal force acting on this ladder. So what actually happens in practice, you can, just take a pencil even, lean it up against a wall, prop it up against a wall, and let it drop. You'll see that what happens is it does not, in fact, fall straight down, as my blue arrow here implies. It actually pulls away from the wall. Right? So by the time it reaches the ground, it's not flush up against the wall anymore. It's over here. And as soon as it pulls away from the wall, it's not a right triangle anymore. And if it's not a right triangle, the Pythagorean theorem doesn't apply, and our whole model starts to break down. Okay, so I'm not saying our method is invalid. This related race problem, we can answer a lot of different questions with it. For example, our heating question from the first slide. What I am saying is that, like all mathematical models, you always have to step back and ask yourself, does this really accurately model what's happening in the real world? Okay, so what's next? We've got one more topic. One more application I want to talk about is something called Newton's method, and this is another one. This one's really kind of for the engineers in the room. Sometimes you have an equation and you need to solve it, right? Even something relatively straightforward, like x cubed plus x minus 1 equals 0. And you don't have any mathematical tools that will work. Right? There's no way to factor that. There's some things you can try. The Cart's rule of sines, rational root theorem. There are some tools you can pull out, but it's entirely possible that there really is not going to be a way to solve the equation that you're looking at. So what Newton's method does is it gives us a really efficient method for finding a decimal approximation of the root. That's why I say this one is a little bit for the engineers, because in engineering, quite often that's good enough. You don't need the exact answer. You just need the answer to a certain level of accuracy. And Newton's method is going to let us do that. It's going to let us get that kind of answer to the question.